So, welcome again to the new lecture of the course Fundamentals and Applications of Dielectric Ceramics. So, let us just briefly recap what we did in the last lecture. So, in the last lecture we started our discussions on ferroelectrics. Ferroelectric materials are those materials which are non-centrosymmetric, which have a polar axis, unique polar axis, and the polarization along that polar axis is reversible by reversing the direction of electric field. In addition, they have a phase transition at a temperature Tc below which they are ferroelectric and above which they are paraelectric, and then they also show they show a, so basically you can say that the polarization above Tc is 0 at E is equal to 0, and polarization at less than Tc is plus or minus Pr at E is equal to 0, and they show a characteristic hysteresis loop which is something like this. So this is a symmetric hysteresis loop. Let me just maybe, and so this is polarization, electric field. You have an eminent polarization at 0 field, and you have a saturation polarization at maximum field, and then you have a electric field which is coercive electric field. So you are forcing the material to come to 0 polarization state, that is the coercive field. So this is plus or minus EC. So it is minus EC, not plus EC. And this is manifested in the form of energy wells. So at ferroelectric show, let me just, ferroelectric show a sort of energy. So this is G as a function of X, let us say. So in the ferroelectric state you have either of one state available, this is plus Pr or minus Pr. So atom goes to either of these two positions, and in terms of applications it is also denoted as 0 and 1 state. So one state is 0 state, so it is basically used for binary data storage, that is why it is called as 0 or 1 state. But nevertheless it is basically the position which is either plus X or minus X position at which the titanium central atom. So basically an anion is shifted with respect and cation is shifted with respect to an anion polyhedra center by a small amount, giving rise to a net dipole moment. And this switching behavior of a ferroelectric can be explained in terms of change of free energy wells. So at very high field the wells will become like this, okay. So all the atoms will basically, in fact it will become like this. So all the atoms from here will jump into this. So this will give rise to plus Ps, and at minus Ps you will have reverse situation, you will have situation like this. So all the atoms will shift here, this will be minus Ps, this is plus Ps, okay, and the intermediate situations will happen as per the movement of the atom in the wells, and then correspondingly you will have 0 Pr or plus or minus Pr, okay. So this is what we looked at last time. Now let us look at a little bit more details of ferroelectric materials. So ferroelectric materials follow what we call as Curie-Weiss law. So basically this law is depicted as the susceptibility of a ferroelectric follows this behavior 3 Tc minus T minus Tc, okay, or you can see that it is nothing but 3 divided by T divided by Tc minus 1. This kind of behavior is, or you can say that 1 over chi is equal to T divided by Tc minus 1 divided by 3. So this is the behavior that is followed by ferroelectrics. 1 over susceptibility is inversely proportional to the Tc, or 1 over chi is proportional to temperature. This is manifested in change in polarization. So at T is equal to Tc, at T less than Tc, a ferroelectric material will show you a hysteresis loop like this, okay, something like that. So this is P, this is E, and it will have plus and minus PR at 0 field. When you go to a temperature T greater than Tc, the material will show a behavior something like this. This is basically a paraelectric. So, you will not observe any sort of finite polarization at 0 field when you are at a temperature above Tc, and this is a typical ferroelectric transition that you should see. This is also manifested in what we call as dielectric constant. When you measure what you do is that when you measure dielectric constant as a function of temperature, the dielectric constant increases, reaches enormously high values and then slowly decays. So, this is your ferroelectric state and this is your paraelectric state, and at Tc it undergoes abnormally high values, and this is because of change in properties such as when you measure polarization, the polarization it drops at T is equal to Tc, and the susceptibility, the 1 over chi goes in this fashion, this is 1 over chi. But this is not the only way it happens, the polarization may drop in this fashion, polarization may also drop in this fashion. So, you may have a vertical line at Tc, the polarization will decrease and then suddenly go boom. So, you can have different ways in which polarization will drop. There is a gradual drop in polarization at Tc, there is a sudden drop in polarization at Tc, and that depends upon the nature of phase transition. So, if you have gradual drop in polarization at Tc, it is mainly because when the materials have second order phase transition, but when it is a sudden drop, then you have first order phase transition. Second order phase transition is generally more gentle in nature, whereas first order phase transition is more destructive in nature or more radical in nature. Similarly, if you measure the susceptibility, in the second order susceptibility shows a dip, but it does not show a discontinuity. In the case of first order transition, the susceptibility will show a discontinuity. So, the susceptibility in the second order will have, first order will have a behavior like this. So, this is the behavior of susceptibility in case of first order transition. So, this is second order and this is first order. So, this is P chi, this is first order and this is second order. So, basically the temperature dependence of polarization is what the nature of temperature dependence of polarization and susceptibility are determined by the type of phase transition that is present in the material. So, we will look at that in thermodynamic aspects of these materials, but basically no matter what the ferroelectric is, ferroelectric undergoes a Curie transition or phase transition at a temperature Tc. Above Tc the ferroelectric nature disappears, material becomes paraelectric, and the susceptibility dependence is given as T over Tc minus 1 divided by 3. This is purely in, this is mainly in case of and this equation is valid only in the paraelectric state, it is not valid in the ferroelectric state, and it undergoes a Curie transition where epsilon value of dielectric constant reaches a maxima before it starts decreasing further, and then the polarization and susceptibility also show a transition at. So, let us first look at the derivation of the proof of Curie-Weiss law, the equation that we have written, before we get into the thermodynamics of phase transition of ferroelectrics. So, let us first look at the Curie-Weiss behavior. In ferroelectrics. So, now basically what is happening is that in ferroelectrics at when you have 0, so we are saying that you have dipole moments like this, when you apply electric field, these dipole moments get aligned in one direction, okay, and this gives rise to what we call as high polarization. But this can happen in any material. In ferroelectrics, what also happens is the interaction between these dipoles. So these dipoles are not non-interacting, rather they are interacting dipoles. So we can say there is a mutual interaction of dipoles, and this mutual interaction of dipoles is due to what we call as a local field. So far we have not talked of local field, we have only talked of a macroscopic field, and this local field tends to be higher than the applied electric field, and the interaction between the dipoles leads to higher local field. It turns out, using we have not done the derivation and we probably won't have time to do the derivation, but there is something called as Clausius-Mosotty relation, which gives you local field value as E plus P divided by 3 epsilon naught. So the local field when the dipoles are interacting, when there is a mutual interaction between the dipole, it is little bit higher than the applied electric field, and it can go as E plus P divided by 3 epsilon naught, and higher the value of P in the system is, more will be the local field. So especially in ferroelectric systems where the polarization tends to be very high, this electric field is also tends quite high, okay. So and this happens only when we consider this at temperatures T greater than Tc, where thermal energy is less dominant, right. That is when interactions can happen. If it is thermal energy is dominant, it breaks over the dipole interactions. As a result, then it leads to dipole randomizations and you will not have any dipole moment. So it happens at T less than Tc, where thermal energy is less dominant. So we can write the expression for, let us say, polarization. The polarization can be expressed as P is equal to epsilon r prime minus 1 into epsilon naught into E. This can be given as, let us say, n alpha into E prime, where E now is taken as local field, and we are taking for all the n number of dipoles of polarizability alpha, and a field which is something different, which is not the applied field, which is the local field. Let us say this local field is, so we replace this local field as n alpha into E plus P divided by 3 epsilon naught. So this will become n alpha E plus n alpha P divided by 3 epsilon naught. I can write this in terms of 1 minus n alpha divided by 3 epsilon naught is equal to n alpha E. So P is now equal to n alpha E divided by 1 minus n alpha divided by 3 epsilon naught, okay. We know that susceptibility now, we know that epsilon r prime minus 1 is equal to susceptibility. This is equal to P divided by epsilon naught E, and this is purely in the linear region, right. And if you do that, we get chi is equal to epsilon r prime minus 1. This is equal to n alpha. So we are basically substituting n alpha E divided by 1 minus n alpha divided by 3 epsilon naught divided by P divided by divided by epsilon naught E, okay. So if you do the juggling, E's will cancel each other. So chi will be equal to n alpha divided by epsilon naught divided by 1 minus n alpha divided by 3 epsilon naught, okay. Now what this shows you is that as n alpha divided by 3 epsilon naught tends to reach 1, what happens? The chi tends to reach infinity, or you can say that 1 over chi will become 0, and that is what we have seen, that at the phase transition, near the phase transition, near the ferroelectric transition, the ferroelectrics show very large susceptibility. So, when you look at 1 over chi as a function of t, this is what you see, 1 over chi tends to be 0, you can see that chi will become very large. Okay. So, chi will become in this fashion, it will diverge at that point, right. So, when you measure dielectric constant, the dielectric constant goes as this, right. So, this is, let us say, dielectric constant, and dielectric constant is nothing but 1 plus chi, right. So, this tends to diverge at t is equal to Tc, that is very large susceptibility, or 1 over chi will show a dip. So, at this point we basically have to ignore all other contributions such as electronic and ionic contributions as well as interfacial polarization. We assume that alpha d is much higher than alpha e plus alpha I plus whatever else, alpha interfacial and so on and so forth. So, at t is equal to Tc, this alpha d is extremely high, and hence we can write this alpha is equal to alpha d, this is equal to C divided by kT, where C is the Curie's constant or Curie constant. Okay. We saw that alpha came out to be some number divided by kT, right, and so that is why we are saying that alpha is equal to C divided by kT, where C is Curie constant, and hence we can write now n alpha divided by 3 epsilon naught, this can be equal to n divided by 3 epsilon naught into C divided by k Tc. So, this will happen at t is equal to Tc, right, that is when it approaches 1, right. So, then we can write this Tc can be equal to Nc divided by 3k, this is kb, okay, kb epsilon naught. So, below this Tc we can say the polarization is there. So, we can say that below t less than Tc polarization is finite, and t greater than Tc polarization is 0. Okay. So, this means that dipoles will align, and this means that dipoles will be random dipoles. So, what is then Tc? So, Tc is equal to Nc divided by 3, and we can write the C in terms of alpha d kT. So, if you write now, if you replace the value of C, this will be Tc is equal to n alpha t divided by 3 epsilon naught, and or you can say that Tc divided by t is equal to n alpha divided by 3 epsilon naught, right. So, this is a general expression, right. So, we have said that using this at t is equal to Tc, Tc is this. Generally speaking, this is the relation that is true. So, now you replace this C in terms of capital T for general temperature. So, Tc by T, not Tc, Tc by T will be equal to n alpha divided by 3. Now, if you modify this and put it in the expression of susceptibility we worked out as n alpha divided by epsilon naught. So, it was equal to n alpha divided by epsilon naught divided by 1 minus n alpha divided by 3 epsilon naught. So, now all you need to do is that just put in the values there. So, it will become 3 Tc by T and 1 minus Tc by T. So, this will become 3 Tc divided by 1 T minus Tc. Okay. So, this is what basically is the expression, that is Curie-Weiss law, which is applicable only near Tc. Okay. In the when we consider the linear relationships and so on and so forth. When the relationships are non-linear, it is not valid, because remember we have relied on the expression chi is equal to epsilon r minus 1, and this is equal to P divided by 3 epsilon naught. So, we have assumed that it is working in the linear region. So, basically this expression is valid near Tc only, nowhere else. So, if you now look at the temperature dependence in totality, so let us say we have a material with, so we have barium titanate example, which has a transition at nearly 120 degrees centigrade. I may be a little bit wrong, but let us assume it is 120 degrees centigrade. So, or some material ATiO3. Okay. So, Tc is this. So, as you start from very low temperature, let us say you start from minus 150 degrees centigrade. At minus 150 degrees centigrade, you will obtain certain ferroelectric hysteresis loop. Okay. So, this is certain hysteresis loop. As you go to little higher temperature, what will happen? A little higher temperature will lead to slight change in the polarization loop, but nothing significant will happen. Okay. So, you might have some reduction in P because you have gone to little higher temperatures. So, thermal interactions will reduce the P. So, they will reduce some P, and as a result the voltage that you may need to apply to align them will also increase. So, as a result your E will increase to achieve the same polarization, and you keep doing that process until you reach. So, this is let us say at minus, I do not know, 20 degrees centigrade, alright, and this could be at certain temperature. So, this is basically, you can say, let us not write the temperature, let us just write T less than Tc. So, let us say T1, let us say T2, okay, that is more appropriate. Let us say this is T2, this is T1. So, now let us go to a temperature T3, which is higher than Tc. So, when you go to higher than Tc, the material will show this kind of behavior. This is Tc, T3, this is Pe. Somewhere in between T1 and Tc, what will happen is that the polarization will keep decreasing. So, as you plot this for other temperatures, the polarization will keep decreasing a little bit. So, for example, it will become like this, then it will also become so let us say these are the temperatures, intermediate temperatures, either all. So, this is let us say for a temperature T1, let us say this is T1 prime, this is T2 prime. So, T1 double prime, and this T1 is lower than T1 prime, is lower than T1 double prime, is lower than Tc. This is how the behavior will evolve, and then eventually you will reach a paraelectric state. So, this is how you can see the polarization as you plot as a function of temperature. It will show a decrease before it goes boom low, or it might show a behavior in which it will be a little bit gradual, something like this. Both the behaviors are possible. So, from this you can also determine what we call as from the change of polarization as a function of temperature, we can determine what is pyroelectric coefficient. This is delta P S divided by delta T. So, you can also determine what is polarization pyroelectric constant for a given material, because we know that every ferroelectric is a pyroelectric in nature. So, basically what will happen is that so what will happen, what are the key takeaways? One, you will have a phase transition. From a temperature dependence. So, as you go from T to Tc to high T, okay. So, this is low T, this is Tc to high T. So, we are looking at the heating process, okay. So, phase transition from a non-centrosymmetric to a centrosymmetric phase. Okay. So, basically large change in the electric constant at Tc. So, this will be change in, so when you take the X-ray diffraction pattern of such a material, let us say, so this is I versus theta. So, in the cubic state, if you look at, for example, 100 peak, in the cubic state 100 peak will be, so let us say 200 peak, okay. You will have single 200 peak. When you take a temperature dependent XRD, this will show a splitting. So, you will have a 020 and then you will have a 200. So, this is cubic and this is tetra. This is how you see study the phase transition. So, this will be 200/020 and this will be 002. So, you will see a clear peak splitting. You will have a change in the XRD peak profile because of phase transition, and this phase transition is because of subtle change in the crystal structure which goes from non-centrosymmetric to centrosymmetric, that is from tetragonal to cubic. Okay. So, this is what you will see in the high temperature region, the cubic region, and this is what you see in the low temperature region, that is tetragonal. So, this is and when you make the electric constant measurements epsilon r versus T, you will see a large change in the electric constant. This is at T is equal to Tc. These are experimental verifications which are done easily, okay. And then we can say a large change in the susceptibility also, right, susceptibility, that is similar to, and then polarization drops to 0 at T greater than Tc. How it will drop to 0? It will depend upon the nature of phase transition, but it will drop. So, you have a phase transition, you have large change in the electric constant, you have large change in the susceptibility, and you have a polarization change. These are few signatures of ferroelectric transition in ferroelectric materials that you see when, and material which was like this, it will convert into sort of a linear dielectric. It's not a very good straight line, but okay. So, this is at T is equal to Tc. So, these are signatures of phase transitions in ferroelectrics. These are certain things show, and remember, this PE loop is not a transitory phenomena, it is a permanent phenomena. So, if you measure the polarization hysteresis loop again and again and again and again, several cycles, several months, several years, it should remain the same at the same temperature, of course. So, I mean, that is why temperature materials which have Tc's near room temperature, they are difficult to establish, because in a country like in colder countries, the summer temperature may be 30 degrees centigrade and winter may be -10, and if you do not have heating in the houses, in winter something will be ferroelectric and in summer it will be paraelectric. So, that is why there were a lot of confusions in the early stages, especially in places like England and America, where a lot of people were working on these materials. They could not determine materials, but then when they made the measurement at constant temperature, they found no, they did have Tc's close to room temperature, and that is what. So, these are the observations that one makes when you make measurements close to across the Tc. So, this is what a brief information about ferroelectrics is. In the next lecture, we will discuss the thermodynamics of these phase transitions of two types, and how the susceptibility and polarization vary across the transition temperature. Thank you.